Hi everybody. Welcome to GPU Force, the Guide to Hardware Acceleration. I am Royi Benyossef, and if this session sounds familiar, it's because I did a similar one at Mobius in 2015. Few changes from last time, so we'll see if... Did anybody attend that session? Does anybody remember that session? Good, because it was crap. No, just kidding. So, introduction. For those of you who don't know who I am and why you should listen to me, let's start with introduction. So I'm Royi Benyossef. This is my face. The same shirt, by the way. This is from I/O 2017, where the pinnacle of my career is speaking at Google I/O. I have been an Android developer since 2009, a paid Android developer. I started before that for free. I did a lot of community speaker stuff worldwide, Joy-Con, Mobius, Google I/O, etc., etc., etc. I'm a mentor at pretty much everything and anything that calls itself an accelerator in Israel and in the US. I have been a Google expert since December 2012. I am actually, I like to say that I'm the first, but that's only because it's nothing official. Don't repeat that. It's just because I haven't found anybody who claimed to be an Android expert before that, and it's probably because the founder of that program is a good friend of mine, so he didn't have any standards when he started. So you could say that I'm the first one until I am proven wrong. I am now the Ecosystem Relations Manager, which is a title I made up, at Samsung Next Tel Aviv. I'm also an investor at Samsung Next Tel Aviv, which is, if you don't know what it is, and it's probably irrelevant to you because we're not operating in Russia anyway, but it's an innovation arm for Samsung that's focused on software products and services. We do investments. I'm a principal in the fund. We invest from pre-seed to B rounds. We do independent product creation, which is as ambiguous as it could be. And we do partnerships and M&A for Samsung Next in anything and everything that is software products and services and has no connection to any Samsung business units. So if you have a killer app that you want to distribute on Samsung devices, do not come to me. I have no connection to any business unit. We have our own products in edge computing and in the deep learning developer tools, et cetera, et cetera. And as I said, I'm a principal in the fund. I invest in startups. So let's start a little bit about what we want to talk about. So what do we want? We want to understand how the GPU works. Now, why would we want that? Who cares how the GPU works? So the answer to that is that when you understand how it works, it's better for you to understand and to construct smoother animations, sleeker transitions, and to understand, to avoid really strange bugs that could arise in different devices. Because the problem with hardware acceleration is that it relies on the GPU. And we're going to explain that logic in a second. Hardware acceleration is a generic term in which you're using a specific hardware device that was created to do a specific stuff or task faster. In our case, we're using the GPU to render graphics in apps or draw the canvas with the GPU by using what Android called in the very, very creative name, the hardware drawing model. That is, instead of using the CPU, which I bet you all know what that is, by using the software drawing model. Again, very creative naming. The GPU, as I said, is specific hardware. It's designed for rapid mathematical operations on matrices. And that's good because the original intent of graphics is bitmaps. Bitmaps is essentially a matrix of saying with some sort of code what color exists where. And manipulation of graphics in animations and scaling and whatever it is, it's actually multiplications of matrices. That is also why it's also used in the last couple of years for neural networks, because neural networks are essentially matrices and have binary operations on them. Now, that's just basic for you to understand why we're doing. So let's talk about the software drawing model and what it does. When invalidate or post-invalidate is called anywhere throughout your app, it immediately starts doing the following. It calculates the dirty region, which is the region that needs to be drawn again, by invoking the calling view, which is the stuff that you want to be changed, but also anything and everything that intersects with it, no matter how deep that is, even if it hasn't changed at all. Now, it's bad, obviously, because it means you're drawing a part of the screen again that hasn't changed, so the performance would suffer. It's good in a way because a lot of you and me included, are built custom views and did not manage invalidate correctly. So if the layout here did not change what was supposed to change, so you should have called invalidate, but you didn't see a bug. It happened anyway because it's intersecting with the same view that worked. That is why a lot of applications, when they started working on devices from API level 11, 14, 16, where hardware acceleration was slowly introduced, started seeing very strange bugs. Views did not render correctly, and they said, oh, it's Android's problem, it's Android's fault. A lot of them came to me as an Android expert, and I found out that they didn't call invalidate in their custom views. So if you still have it on some devices, that's the reason. So good-ish is that it hides your bugs. After it calculates that region, it immediately draws it by using the CPU. And that's good, because the CPU is exactly the same for everybody. The Snapdragon works exactly the same like the Samsung one, which works exactly the same like not the Intel one. All the ARM ones work exactly the same. So it works the same way wherever you use it. And it exists on all the devices that you use, because a device without a CPU is, I don't know what that is. It's not a phone. It's not a smartphone. It can't run Android. The bad thing is that it's slow everywhere. It's predictably and ubiquitously slow wherever you go. And there's a very good reason for that, because it's also in higher demand, because stuff that are not graphics are always on the CPU. Stuff like populating objects or accessing databases or calculating anything that's not graphics. So when you have something that's a jack of all trades, when it can do a lot of stuff but slower, and a lot of people are coming and asking for it to operations, your time in the queue, the time that you wait will be longer, so it's slower twice. So as we said, the software drawing model is immediate, which is a problem. We're going to discuss why in a second, but it's also inefficient. The hardware drawing models works in the following way. When invalidate or post-invalidate is called, that view is flagged as dirty, and the changes that need to be made are written in something called display lists. And upon vsync, that happens every 16 milliseconds, does anybody here wants to shout out why 16 milliseconds? Does anybody know? Raise a hand if you have an inkling. Yes?
Because Android draw in 60 FPS.
That's right. In order to reach 60 FPS in animations, you need to have a frame drawn correctly every 16 milliseconds, so Android called it the vsync. It uses the GPU. That's good because it's faster, because it's dedicated for graphics. It's built specifically for that. It's not as used because it's only for graphics and AI, but mostly for graphics, especially on phones. And in properties like animations like alpha and rotation, which are essentially multiplications of specific attributes of matrices, it doesn't need to invalidate at all. It simply changes something in the GPU, so there's no upload again. There's no sync, and therefore there's no invalidate, so it's even faster. The bad is that support is specific per device or per GPU or per API level, and it's absolutely non-standard. You could have two phones. Actually, there is a phone by an OEM that shall remain nameless that has half of the model with a specific kind of GPU and the other half with a different model. Everything else is the same. Same device, same firmware, same API level. Applications behave massively different because the GPU is slightly different, so it updates slightly different and it screws 50% of everything that you do. 1 second. And it does not hide your bug. And the last thing, which is important, is it uses more RAM. Now, the reason that it uses more RAM is because in order for something to move from the CPU, like the mathematics, to the graphics, to upload, it needs something. It is done by the random access memory. So if you need to work on the GPU all the time, you need more RAM because the device needs RAM for everyday usage, and it also needs RAM to funnel into the GPU. And the RAM is expensive. So hardware drawing model is faster and less predictable. Okay, I just gave definitions. We didn't come to the problems yet. So what's their fix? We need to understand when should we use each model, And herein lies the question, why shouldn't we use the hardware acceleration every time? I'm going to answer that question. The second thing is to provide predictability about when would this hardware model work every time and when you should troubleshoot and see why something could be wrong on some devices. And the last thing is to actually do the debug and troubleshoot. So, predictability. How can you get it? Sorry for the coughs. So, API availability. The hardware acceleration has only been around in Android since API level 11, which is 3.0, where tablets first showed up. Now, the reason that they needed to start supporting hardware acceleration was that the screen got bigger. When the screen got bigger, the CPU could not handle all the graphics that it used to, because before that, we have very small devices with poor resolution. So, but between API levels 11 and 14, which is 3.0 and 4.1, we had support, and there's a reason why it's in quotes, but the default for hardware acceleration was off. They only put it on for specific things, and part of the reason for that was the actual support. The second thing is that those devices still came out to the market with very small amounts of RAM. So if you plugged it up for everything, the device will explode, and not in the Samsung Note 8 explode. It would actually burn up. So after API level 14, devices were mature and everybody were happy. So the support got better and the default was on. In terms of support, in order to support hardware acceleration on a device, you actually need to implement specific commands of OpenGL ES in the canvas implementation of the firmware. That's something that takes a lot of time to implement. And the implementation is very different between one GPU and another, and one device and the other. And the implementation is complex. There are a lot less OpenGL ES developers on Earth than they are Java or Kotlin or whatever it is that you're developing in right now, or React Native or JavaScript, et cetera, et cetera. So you need to find these people. It takes longer to work. The QA is more troublesome. So what they did is that they started with the basic standard views first. And that's good as long as you use the standard views. But when you started using custom views, if you put in a call that is not supported on the device and the hardware acceleration was on, you got really strange stuff like invisible UI elements. This is an actual example from a product that I was the group leader of the startup that since died, and it built a television box, a set-top box based on Android, which is my area of expertise. And in the onboarding screen that some of you may come to understand that you know because it was released in Russia 3 years ago, when you clicked down on the remote control from this button, you actually saw this strange stuff, because the stuff that was supposed to be illuminated, and I apologize to the cameraman, this was supposed to be green just like this is, only it didn't happen. You had this green ghost thing and you had nothing here because the element itself was invisible, and it took us 2 weeks to understand why, which is also part of the basis of why I started writing this session. Badly rendered pixels. Again, an example from the actual product. This was supposed to be a gallery, an OpenGL ES gallery that was, it looks like shreds. We actually called it Wolverine because it looked like somebody shredded the screen. And you might not realize, but there's the whole alphabet here for some reason. Very, very, very strange. It only happened on specific devices. It only happened in specific instances. It took us a while because there's nothing in the debug mode here that will say, I know exactly what that is. There's absolutely no way. And that is, again, the reason why I started this session, so you'll have a bigger chance of understanding what's happening and fix it or even prevent it beforehand. Last thing is exceptions, mostly memory-related exceptions, like memory leaks that you can't find, out of memory, out of bound exceptions that make no sense inside the firmware that you don't understand why. This is what we're coming to examine. So, for predictability, if you're using the standard views and you're not using any custom views whatsoever, how many people here are using only standard views? Okay, just to make sure you're listening. How many people are using some kind of custom view somewhere? Okay, so it seems like you're listening. So so if you are only using standard views, you're completely okay. If in the custom views your calls are supported by the API on standard Android tested devices, or by using this list that is on the Google developers, the Android developer site, so you can actually see what's supported on each API level, you're good. You're supported. You don't need any continuation of this session. However, if you did not check this list, and I would bet that 90% of you have never heard of this list, then we need debugging. So let's start with the tools. Rendering. Rendering tool is basically measuring how big is your GPU and how it's functioning. To profile it, you can either use Android Studio testing suite, or you can do it on the device. As of API level 16, you can go into the developer's option and test it on the device. You must have seen this graph 100 times in different sessions. I bet no one explained to you what the actual graph means. So we're going to do that here. So it displays a graph of the visible app, and the vertical bars, each bar is a frame that was drawn. The height of the vertical bar is time in milliseconds. So the higher it is, the more time it takes. The color of the part of the graph is actually a stage in the pipeline of the GPU. And I'm going to go through each and every stage because each of them would tell you to look somewhere else in your code to see what's wrong or if something is wrong. And that actually changes by API. So I'm going to go through the stages that are API level 16 and upwards, because basically if you're working on devices that are API levels that are lower than 16, I pity you greatly. But it's also on the developer Android side, and it's pretty much the same thing. The vertical line, the little orange thing that you're probably seeing there, it's the 16 milliseconds that we mentioned earlier. Why 16 milliseconds? To reach 60 FPS. If, like the poor person on that drawing, all of your frames are above 16 milliseconds, their app will look like, pardon my French, crap. So the diagnosis is, graph is over the line, there is a problem. Now, let's go through the stages and what to do. This darkish gray thing is actually called input. It's on the bottom of that graph, and it handles the input events. So anything and everything in rendering in input events will be drawn in the somewhat gray like this. And if it's too long, it means you need to go through each and every callback for input and see if there's not too many tasks in it, or there are not any things that you can put in the background thread. Because it's on the main thread, it's stopping it from going to the CPU and then to the GPU, and it might be too big. So if the gray thing at the bottom is too long, look for the input event, the on callback for input. The slightly brighter gray, they're not creative with colors as well. I don't know what's happening to Google. They're so colorful in the logo, but yet, dark gray, a little bit less dark gray. So this is animation. It's the time where the animation itself is running, just running, without anything else. If it is too long, you need to go and check the animation callbacks in classes such as Object Animator, or View Property Animator, or Transitions. In most cases, I'm referring to these classes because in most cases, the graph that you saw is in property changes, like what happens when the recycle view is flipped. And in most cases, the animation is actually skewed because of the population of the line item in the recycler view, or the fling, or when you move a view left and right. So you would go into the animation callback, and then you will see that it refers to the recycler view, and you'll see that it is waiting for the object to propagate. In most cases, you would put that in a better background thread, and you will resolve the situation, or you will do other stuff that I will talk about in the tips at the end. The slightly lighter gray is measure. I'm sorry, I didn't pick the colors. I'm actually colorblind. I don't even see that. I asked my wife to check the coloring. Measure is the time that it actually takes Android to calculate and measure all the views that are on the screen all the way up to the root, so they can organize the views before they draw it. If that is too long, it means that either you added code in your custom view to the unmeasured or unlayout that could be in the background or could be somewhere else, or you need to debug your hierarchy and check for overdraw, which are two things we're going to focus on separately. Draw, which is this kind of bluish something, is the time that it actually takes the rendering itself to happen, If it is too long, you need to check the code in the onDraw or dispatch draw of your custom view, or you guessed it, you need to debug hierarchy and check for overdraw, which we're going to focus on later. Upload is the time it takes to load the bitmaps from the CPU through the RAM into the GPU. It's impacted by the sizes of all these three things. So to give an example to illustrate what I'm saying, if you brought your car home after grocery shopping and you want to unload the car and put it in the fridge, or at least get it to your apartment, you are the amount of times you will go back and forth is dictated by how big your car is, or how much stuff you put in it, and how strong you are to try and make it in one go, as I do because I'm lazy. So the more that you bought, the longer it will take you because you need to go back and forth. And again, the size of your arms also dictates. And finally, actually, the size of the apartment doesn't really matter here unless you're living in a cardboard box, but allegory aside. So if it is too long, you need to try and understand if you're not abusing the random access memory. So try and look at how much scaling you're doing. Maybe you need to supply specific bitmaps that are correct to the screen size and avoid scaling at real time, which will take back and forth between the CPU and the GPU. It's that kind of stuff. Trying to standardize it in a way that makes sense. Also, take advantage of Prepare to Draw. Prepare to Draw was introduced in Android N, and it actually allows you to draw into a texture buffer before and just switch it in real time. It will actually save you a bunch of time in this specific way. Just Google Prepare to Draw and you'll find a lot of guides to do that. I actually wanted to focus on that, but we have 250 slides and only 60 minutes. So, last thing is check for overdraw, which we will address soon. Now we're looking at, is it green or is it orange? I don't know. Issue, which is the time it takes to draw the display lists, which are different between screen to screen, and swap, the time it actually takes to swap buffers that were prepared beforehand. Both of those are impacted specifically by how many commands are there in the display list. So if you, in your custom view, if you have the top command, which is very stupid, no one will do that, but it's a stupid example to illustrate my point. So if in your custom view, you have the canvas draw point running like this, and you replace it with this command right here, which does exactly the same, the bottom half will actually take 1/5 of the time of the top half. And that is, now, why would you have that kind of ugly code? Because you copy-pasted it from somewhere and you didn't think about that, because you're saying it works exactly the same, only it doesn't. So if you have things in your code like this, and the two parts, the orange and the yellow, are too big, try and replace them. It will help you greatly. The last, it's actually the first, but I don't want to start from miscellaneous. It's actually the very bottom is the really, really dark gray. It's anything and everything on the main thread that has nothing to do with graphics. So as I said, access to database, calculations, movements of any kind, population of the JSON object into the Java object, etc., etc., etc. If this area is too long, then obviously something on the main thread should not be on the main thread. And for some reason, you didn't get the exception of not on the main thread or something. So you need to go over it and see what's going on, because that's the basis for everything else. You can also use systrace or tracer to find that, because that will be very difficult to debug with the overdraw and the hierarchy view that I'm going to focus on here. So, overdraw. How many times is too much? There is a tool, it's been around for ages, to debug GPU overdraw. This is the app that you have, that someone has, and you can see it's okay. I mean, it's basic. But when you start the debug GPU overdraw in the developer's option menu, you'll start seeing colors. So the blue color means that every pixel was drawn twice instead of just one time, which is what you need. Green will be an overdraw of 2 times, pink will be 3 times, and 4 and over would be red. A lot of the apps that I've examined through mentoring sessions that I did with developers started looking like this. And that's after me talking about overdraw for at least 4 years. So either I'm not broadcasting enough or people are not listening. So the diagnosis here is that when the same pixel is drawn more than one time in one frame, it's redundant effort for the GPU. Why? Because you actually need to, I'm going to explain how the GPU works here. You actually have two buffers referring to the same pixels. So it takes longer to measure because the GPU understands that it's not completely measured, so it waits for the end. So it measures twice and then it uploads the same texture twice. So it's a lot of effort on the GPU, and that's why overdraw is problematic. So fix whenever possible. How should I fix that? Very easy tips. The default for all of the layouts is that there is no background. But in most tutorials of Android, even today, the first thing that they teach you is to put in a background. And that's stupid, because you're essentially creating a layer that in most cases nobody sees. So if I'll provide an example here from an actual tutorial that I looked at, there's a relative layout that holds two image views. The relative layout has a background. The image views obviously have a background because they have an image. So now you have three layers and you're only seeing one, because you have the background, you have the relative layout, and you have the image view. So when you put in the overdraw, you'll see the pink reddish something, and by simply stating set background false or to make it completely invisible and reduce the overdraw, people are actually having jank in their applications and they don't know why. So this is the reason why, very easy to fix. Layout Inspector, which came out about 1.5 years ago, is exactly what you need to use to qualify these kind of situations for things that are not as obvious as this very, very simple example. So simply use Layout Inspector and you'll see exactly what is between you and the screen that you're seeing, and you'll get a lot of benefit out of it, trust me. Another thing that you need to think about is to flatten view hierarchies, which is the way that you get there is to debug the hierarchy, which we're going to get to right away. But you also need to reduce transparency. Why? Because it's a background. Transparency is actually something you don't see, but the GPU does, because it's actually an alpha property that's being loaded twice, and it takes twice to measure. Why? For the same reason, because you can't see it. The GPU waits until everything else is drawn, and then it comes back and measures it again to make sure that you're not seeing it. So it takes the 2x amount to measure, which would appear on the GPU rendering tool, and the reason will be alpha. Now, after I did like a trailer for debug hierarchy for so long, this is it. This is the money shot. So hierarchy is represented in a logical tree. Right? You remember the old hierarchy viewer that you saw the actual trees? That's actually how Android looks at it. And it has the same complexity calculation as a logical tree that I bet most of you learned about in the university that I got kicked out of. So tree iteration is impacted by two things. It's impacted by the tree depth, the amount of steps that you need to have on the way, or the height of the tree, and the amount of iterations that you need on specific node types. Now, you're saying, how can I impact that? Well, here's your answer. Tree depth is the amount of nested views. So the more you have linear layout inside linear layout inside linear layout, the worse you get. In fact, if you have a nesting group of 7, your device will most likely catch on fire, even today. The opposite of that is that to reduce iterations, you need to decrease the amount of relative layouts that you have in your view. So you're saying the biggest suggested solutions up until 2 years ago to solve hierarchy functionality was to use more relative layout. Why? Because it's flatter. Only when you use relative layout, you're actually creating double taxation. What's double taxation? In the view hierarchy, you will get to relative layout, and then it will go to its sons and try to understand exactly what's in the view, because it needs to, in order to understand relative layout, you need to see all the sons to organize them specifically, because they're all relative one to another. So it's actually measuring between 2 and 8 times more or times than it would with the linear layout. So it really depends on what you're doing. If you have a really nested view that you can replace with one level of relative layout, do it. If you're just replacing it and you're just replacing one or maybe two tiers, don't do it. The best thing you could do actually is troubleshoot, which is remove redundant nested layouts, which I started saying. Lint can help with that, by the way. The lint is very helpful. You can see that here you could replace a frame layout by a merge tag. So it's not even a layout. You'll reduce the layout completely, and inspect code is actually very helpful here. You need to adopt, as Lint pointed out in the last example, merge include. Do any of you think they know why? Raise your hands, don't answer. Do you know why? Okay, after that I'm gonna ask you if you were right, which is a stupid question because of course you would write afterwards. Include to layout actually creates an additional layer. It created another nested layer inside the layout inspector. But if you put merge in, it actually pastes it in. It does not create a new layer. It pastes it on the old node, and then you only measure it once, and therefore it is better. The last thing is to adopt a cheaper layout, which, as I said before, is complicated. Because if you have 4 tiers of linear layout versus one relative layout, is it better? Is it worse? It's kind of hard to calculate. So the best thing to do to flatten hierarchies is to use non-relative layouts, so it will reduce iterations. And if you're using constraint layout, that's great because everything is solved for you, because it's a relative layout that's pre-populated, and therefore it's flat, and there are no more iterations. Problem with that is that it starts from API level 24, or if you're using Jetpack, it might go as far as I think level 21 or 20, I'm not sure, but there are a lot of devices that you cannot support. So in those cases, you might need to start using these discarded sons, the layouts that nobody uses. So there is a reason that you probably should use it on low-end devices. Okay, we're in general debugging. So how would you know it's a GPU if everything and anything here has failed you, or if you're just too lazy to do it? So the first thing, if you have an issue that you're getting back on the notification system that only happens on specific devices, but doesn't happen on other devices, because you're seeing a reproduction only on a specific family, that's probably a GPU. If it only happens on API level specifically, and it's addressed to custom views or the neighborhood of custom views, that's the GPU, because the support level is not good enough. If it only uses GPU families, because for some reason you know the spec of each device and you know that this LG and this Huawei are using the same GPU family, and it only happens on these 2 devices, that's the GPU. The second thing you can do is set the scope for hardware acceleration, because as I said, you can turn it on and off based on application activity, window, and layer. So if you turn application completely off and it's solved, then you know it's hardware acceleration. So it's just like looking for a short circuit at your house. You go to the electric panel and you're switching everything off, and then you one by one until you hit the thing that short circuits. That's basically what you need to do here. Just decrease the granularity until you find the culprit, and then fix it, or don't fix it because it's small enough for you to live with. I don't know. I'm not your boss, but here's how you found it. Debug and settle into the right scope. Another tip here is to use the hardware layers, because the layer is the smallest component possible, so you can flick on layers even in lower API levels. So buffer cache, which are a precursor to layers, has been around since API level 1. But at API level 11, they added the layer type. So layer type none has no buffer. It's not saved anywhere, software or hardware, and it's rendered by the software rendering model. The layer type hardware is backed by a hardware texture buffer, which is the one stage before it's uploaded to the GPU. It's rendered in the hardware model. It is best for performance, and animations that are added to the texture are done so without redrawing. Those animations like alpha, I'm going to talk about it a little bit sooner. The layer type software is backed by a bitmap on the CPU, and it's rendered in the software model. It is best for compatibility because it works the same way on any and every API level. And one thing that's not completely related to the layer is that there are two methods for checking if something is hardware accelerated. There's the view is hardware accelerated, and there's the canvas. The view is okay. The view it gives you the right answer every time. But if you're using canvas is hardware accelerated, the window can still be drawn in the software model, even though canvas is a hardware acceleration will say true. I saw a lot of people who are very confused by that and created a lot of bugs, so I thought I'm going to mention it here. Layers and animations is something that's very important. So populating like recycle view to reach 60 FPS is something that's very hard to do. So if you rendered the view into a hardware texture, you just offload how it looks like into a hardware texture, and then you move that texture, which basically does not change, it will be a lot easier. And it's very easy to do so, because then the rendering is just of a texture and not of the actual complex view. And then also property changes will not invalidate it, like transparency, like position, XY translation, like scaling. So remember when I said scaling is a big problem with the GPU? If you do scaling as property animation after it's uploaded to the GPU, it doesn't matter anything. It's free. So there's a very big difference between using alpha, trying to put in alpha as a background, and using alpha in a texture animation or property animation once it's loaded. Rotation and 3D orientation, again, anything and everything that's a multiplication of a matrix is free, because that's what the GPU does anyway, so it doesn't need to load anything. Pivot X and Y. So for all of those, I would urge you to use this way. Instead of using it in a view or having a view animation, etc., simply do it in runtime. And then you will offload it into a buffer, and you just put object animator afloat and do rotation. That's great, right? Well, no, because what I did just now is that I established that this view is hardware accelerated to the end of time. And that's not a good thing, because the next time I would invalidate this view, if it's not intended to do so, it will actually upload the whole view into the GPU again. So the actual pattern that I want you to use is this one. It means that as long as the animation is running, do the hardware acceleration. The minute that it ends, revert back to the layer not being hardware accelerated, because in most cases, it's not only that you don't need it, it will actually hurt you in subsequent animations of that view later on. One other custom view top tip is this. This simple example is something that I actually picked from the Android source code itself. And that's something that Google themselves have never published. And it's very, very, very simple, because I saw that there is an is-in edit mode in the source code. I said, why? Why do we have that pattern? So when I looked, I saw that that's what Google did in API level 11 to 14 inside their custom views. I've added it to every custom views I did between API level 11 and 16, and it solved 90% of the issues with the GPU. It's very simple, very effective. Top tips to finish off. We're way ahead of schedule, so you'll have a lot of time for questions. 20 minutes. I talk very quickly, and you're not asking any questions. So don't create render objects in draw modes. Why? Because the draw modes is called once every 16 milliseconds. And if you're creating new every 16 milliseconds, the garbage collection will come quickly. Garbage collection will choke the whole system, and so avoid doing it. I see a lot of new path, new paint in these methods. Don't do that. Don't modify shapes too often. Why? Because when you modify shapes, you're creating a texture drawable again, which is uploaded to the GPU, which is costly. So create it once the way that you want it, and then just do manipulations like alpha, rotation, pivot, everything that's free on the GPU. Don't modify bitmaps too often, because every time you change the actual bitmap, and I've seen a bunch of people do that because it's a brute force method of animation. If you don't understand exactly what you're doing, it will be uploaded again and again and again to the GPU, which will clog up the GPU, and then the cleansing cycle is very expensive, blah, blah, blah. Use alpha with care, meaning in the right context. If you're using it in property animation on the GPU, that's great. If you're using it as a background, that's not so great because it creates overdraw, and it takes 2x time to fill rate because it will take twice to measure. So in these cases, use the layer type hardware acceleration, and therefore alpha is free. I've finished 252 slides in 42 minutes. I am very proud of myself. Questions? Yeah, we just need a microphone.
Thank you for the amazing talk. I got two questions for you. So with the recent arrival of mobile gaming phones like Razer that claims they have 120 FPS, and do we as developers need to do something about the speed of our animations? Do we need to it's 8 milliseconds per frame now, and
The answer is within your question, because there are some phones, game phones, that have 128 per 8 milliseconds. If all of your clients have these phones, no, do whatever you want. But in most cases, you will have a very, very wide range of clients. And the more you support, the more you have to worry. I mean, if you look at companies like Uber or Get Taxi, they can say, no, game phone only. I only take car rides for developers, and the rest, their app can look like crap. So it really depends on who you're serving.
Okay, thank you. And the second question is about hardware bitmap. Do we need to use it? Hardware bitmap?
If your animations are all custom animations that are built on subsequent frames, yes. Again, it really depends on your usage. If all your animations inside are property animations of custom views that are just a trickier way to do it, no.
Okay, thank you.
Sure.
Sometimes we have a very difficult animation and it's take a lot of time. And can you give us advice about maybe texture view or something else what draw in our chart?
So first of all, I'm going to ask you a question. Did you run the rendering GPU tool that I mentioned? Yes? And which portion of the frame did it say that it had a problem with?
It's very difficult. Have many operation on one bitmap and it's not enough.
Okay, so I would simply urge you to, once this is published, to go slide by slide, and you'll see, because for each of those frames, I gave a different advice. It will be very long and very presumptuous of me to assume what the problem is from what you just told me. But it also sounds like, yes, that you need to go and explore texture buffer animation. Sounds like it to me. But just each and every part of the frame will have a different performance boost that you might need to explore.
Yes, yeah, I understand all these techniques and we use it, but sometimes it's draw in main thread and we have draws in our thread, not main. Or change our bitmaps in our thread.
It's very difficult for me to answer based on the information that you give me. So I would love to help. The organizers can give you my email because I don't have any business cards. Unfortunately, I forgot them at home, but just email me and I'm going to try to help you.
Yeah, thank you for your presentation. And in one slide, you mentioned that GPU may be used on Android phones for some AI purpose. Can you give us some techniques what we should look for if I want to run DNN, for instance, neural networks on Android on GPU, like CoreML on iPhones?
So the TensorFlow, like Kafka, all of them are actually running on the GPU already. And in TensorFlow Lite, there's the open source code that actually you will see the actual code that's running in native, so C++. So you just look at that as an example. It's a very, very good example. It's not optimized 100% because the open source part is a little bit older, but it's a great pattern to start from.
And TensorFlow Lite use GPU on Android phones, right?
So what?
TensorFlow Lite use GPU on Android phones.
Yeah, absolutely.
Other questions?
How does effort for performance clipping views? Clipping
How
on?
much effort? There's some effort. It really depends on what you're trying to do. Clipping as itself, if you clip it in the bitmap before you upload it, it's very problematic on the CPU. If you do it
View
after
container.
view container. So in the view container, basically what you're doing is that you're creating a square in the bitmap on the GPU, so it's buffered to the CPU, and then you upload it back. So it really depends on how much time you're doing it. If you're doing it once in a frame or in a couple of frames, that's okay, but don't push it too hard because whenever you're uploading it again, it takes time from the GPU.